Welcome to the video covering Lesson 4, Proportional Parts in Triangles. The question we'll be able to answer by the end of this lesson is, what do parallel lines have to do with proportionality? So let's suppose that DE is parallel to AC. You can see the little tiny triangles there, and then these are supposed to be straight parallel lines here in between those two segments. So DE is parallel to AC. So if they're parallel to each other, I can take a look at their parallel lines and make this one side AB or DB. I can make this side the transversal. So I have two parallel lines cut by a transversal. And so I've just labeled these angles 1 and angle 2. And they should be familiar, but what that says, and the reason why I'm doing this, is because angle 1 is going to be congruent to angle 2 by corresponding angles. And again, that goes back to the lesson in a previous chapter about the parallel lines being cut by a transversal. Those corresponding angles are congruent. The other thing I can do with this figure is I can split it into two triangles. I can have this larger triangle, ABC, ABC, and then I also have this smaller triangle, DBE. And so because I have these two parallel lines, you can picture that there are two overlapping triangles, a large one and then a small one. And because angle B, that vertex B, is the same, we're going to say that angle B is congruent to angle B. And when something is congruent to itself, that is the reflexive property. So it's going to be congruent to itself because it is the exact same angle measure. We are picturing them as overlapping. So this is important because now I have two angles that are congruent to each other in these two triangles. So I can make the statement that triangle ABC is similar to triangle DBE by the angle similarity. The reason why that's important to create these similar triangles from these parallel lines in the triangle is because now we can use all of the properties from similar polygons that we learned in the previous lesson, that all of their angles are congruent and that their side lengths are proportional. So that example just proves what we are going to state here is that if overlapping triangles have parallel bases, then the triangles are similar and the segments are proportional. There are two types of proportions that are created when when two overlapping triangles have parallel bases. You have the small triangle to the large triangle, and you have segment to segment. So let's take a closer look at each of those. With the small triangle to the large triangle, in red we have triangle GEH, and in blue we have triangle DEF. From the red triangle, GE will be proportional to DE, just the same way that EH will be proportional to EF. So when we're doing small triangle to large triangle, I really want you to be thinking about the whole side. Like we have the whole side of the small triangle, we have the whole side of the big triangle. So with these, again, I really want you to be thinking whole information, the whole side length of either the large or the small, that doesn't matter, but you have whole information. For the segment to segment proportional relationship, I want you to be thinking parts. You have this part of the large triangle, and yes, I understand that this is a whole side to the small triangle, but as far as the large triangle DEF is concerned, we only have this little piece of DG, and we only have this little piece of HF. If you only have parts of the larger triangle, you're going to want to set up the segment relationship. So for this one, again, I want you to be thinking part. So let's see if we can start to use some of these proportional relationships to find missing values. Again, let's compare what we have here. I have a 4 and I have a 3. Now this 3 is just a part of the large triangle. But if we look at the 14 and the X, they are whole pieces. The 14 is the whole side, the X is the whole side, and even the 4 is the whole side. So this is a whole side, whole side, whole side. But then we have this 3. But luckily, we have the 3 and the 4, and so what we can actually do is add them together to get the whole side of 7. So now we have the whole relationship, which means I am going to split the triangles into two, and we have J, N, M, the small triangle, and then we have the larger one of J, L, K, and we can label this information. JN is 4, JL is 7, we just added those together, NM is X, LK is 14. And so what we really end up using is these two triangles to set up a proportion equation where 4 over 7 is equal to X over 14, and we cross multiply and solve. So in this case, X equals 8. So let me walk you through that process again. I decided to do the whole triangle to the whole triangle proportion because I was given the most information about the whole sides of the triangles. I understand that 3 is a part, but with all of the other information being whole side lengths and the fact that I could quickly find the whole side length of that large triangle, I was able to do the whole triangle to the big triangle, so small triangle to big triangle comparison. In this second problem here, we have 8 is a part, 6 is a part, y plus 5 is a segment or a part, y is also a segment or a part of the big triangle, but y plus 5 is the whole on the small triangle, just like y is the whole on the small triangle on this side. The problem is you don't have any whole information for the big triangle. You wouldn't want to, like if you did y plus 5 plus 8, that's just going to get more complicated. You did this side over here, y plus 6, to represent that whole side. It's not that you can't solve something like this, and we could use the proportion that would result from all this simplification, but it's just a whole lot of work. So instead of looking at the whole pieces, we're going to look at the parts. So with these, we're going to use the part proportional relationship, which just allows me to set up y plus 5 over 8 equals y over 6. And I can cross multiply and solve this. So in this problem, y equals 15. So again, when we're starting these problems, we're going to analyze what information is given to us. This x is a whole side, this 6 is a whole side, the 12 is a whole side, and the 8 is a whole side. There's no question in this one at all. All of the given information is whole. So we are going to use the comparison of the small triangle to the big triangle. Okay, so we're just going to take x matches with the 6 the same way that the 12 matches with the 8. So again, the x is on the parallel side, it's matching with the 6, so I put x over 6. 12 is this whole side down here at the bottom, 8 is the whole side down here at the bottom of this small triangle. If you can visualize that without having to actually draw out two separate triangles, you do not have to sketch out the two small triangles. If you're struggling with visualizing it, then I would definitely recommend drawing the two separate triangles. Final example, let's look at what we have here. 15 and 30 are wholes or segments or parts, depending on really the rest of it, because the fact that those are parts of the small triangle. So if I look at the large triangle, I don't have the whole on this side because this is a 15 and this is a y. Yes, I can make this whole thing the expression of y plus 15, but I don't want to do that unless I have to. Looking at this side, I do have the whole, but in that case, what I'm going to do instead is I can take this 42, subtract 30, and make this piece 12. And again, I'm doing that because if I tried to split it into two triangles, where the smaller one is 15 and 30, the bigger one is 42, I would need to make this y plus 15. Not that that's not possible. It's just not the way that I want to solve it. So instead, I'm going to set up a ratio of 15 to y equals 30 over 12 and treat them as the segments, as the parts instead. So So after cross multiplying and dividing, we get y equals 6. Maybe you've made a connection through telling the difference in the look of a problem if you are supposed to use the small triangle to the large triangle ratio or the segment to the segment ratio. And the hint is that if the parallel sides are labeled, then separate the triangle. So we've already done these examples. I'm just pulling from them again. In this example here, DE and AB are the parallel sides. Notice that they are not labeled with a value. They're not labeled with a variable or an amount. But in this example, my parallel sides are labeled with an X and a 6. When you are labeling, when the parallel sides are labeled, that's when you want to separate it into the larger triangle, and that's an X there, and then the smaller triangle with the 6, 12 and 8. So when you have the parallel sides labeled, that's when you want to separate the triangles out to the larger and the smaller triangle. And this concludes the lesson 4 about proportional parts in triangles. So what do parallel lines have to do with proportionality? Well, parallel lines create overlapping similar triangles with proportional sides.